Okay. Teams, no, this one. Okay. Great. Voi che vedete? Ah, vedete quello, ok. No, perché no? This is the... La modalità presentazione. Sorry for... Ok. Probably it should work. Okay. No, era l'altra modalità presentazione. Ok. Let's try to start. Okay. So the last slide that we saw also on Friday, no, on Tuesday morning, when everything was happening, thunders, okay? Okay, so we basically we tried to determine the stability factor for the output voltage of our power supply. And we found this formula here. So basically the stability factor with reference to the input voltage was something depending on, okay, working again, okay, depending on the transconductance GM and the resistance R3. And so we make some consideration about this opportunity. Now, what I want to characterize, to study, is the output impedance of this power supply. Why the output impedance? Because we are interested in the stability factor of the output voltage as a function of the output current IL. Okay, so we want to see how the output voltage change when we change the output current of the system. And if you remember, in a system where we have an output voltage and output current, if we take the derivative of the output voltage in terms of output current, we get the output resistance. Okay. We can consider that this power supply is basically a voltage generator, a real voltage generator. So it is a voltage generator with in series this output resistance. And this is one way to calculate the output resistance, just considering the derivative of the voltage in terms of current. Okay, what we should do now is to rearrange the block diagram of the system in order to have a reference in terms of output voltage and current. So now I go back to the previous schematic diagram that I showed you, the one where we had an output voltage VO, a reference voltage VZ that is created by the Zener diode. Then we take a part of the output voltage using these beta blocks, the feedback block. We get this feedback voltage that is subtracted to VZ, and we use this error voltage as the input for the output amplifier. Okay? So this is schematic that we saw for the first time, the first schematic that we saw. We are not considering anymore the ripple. We are neglecting the ripple. Ideally, this ripple in this study is 0, but we are only focusing to the variation of the output voltage. So if you consider the equivalent circuit, you see that here I removed the ripple voltage. If I go back a few slides, yes, or if this we here. In that case, we used the ripple voltage because we wanted to see how much ripple when passed through the system to the output. Now instead we are not interested in the ripple, so I removed this ripple. If someone or you asks, well, what is it going to happen if we have at the same time ripple and variation in the output system, we can ideally think that we can use the overlap theorem. So we can add the results of the two studies. And so the system will have at the same time some ripple, some variation due to the current. Okay. So the block diagram is here. The equivalent, the circuit that we are considering is this one, where, as I told you, I just removed the ripple voltage here. Now we should consider, we should be able to calculate basically the output resistance when the system has the feedback connected. So our system is a feedback system. So I want to calculate the output resistance when we have actually a feedback system that is working. One way to calculate this, if you remember, is to calculate the output resistance when we don't have any feedback, and then divide by the open loop gain of the system. And we are going to do this in this case, trying to do as less calculation as we can. So we don't want to waste time and doing, again, a lot of calculation. So if you read here, we are able to find the open loop resistance RO, and then we know the the loop gain beta A, we can divide RO by 1 plus beta A, and we find the output resistance with feedback. If we want to calculate before calculating the resistance, we can calculate basically the open loop gain of the system itself. In this case, one should decide where to open the loop in order to do not alterate all the gains. You remember, if you want to open the loop in some place, the total gain must not be altered. One point where we can open the loop is here. You see there's two red lines, two cuts there. Why am I going to open it here? Because basically, if I disconnect this point, the total resistance that is seen by this point, if I look into this direction, is very high. It is high because basically it's given by those two resistances, more or less. And at the same time, the output voltage is not going to change if I close or open the system, simply because those high resistances are not loading too much the output of transistor Q1. Q1 is a transistor connected as a common emitter. So the output dynamic resistance of transistor Q1 seen by the emitter is very low. The output voltage does not change a lot if we take or don't take current from here. So if I connect or disconnect this resistance, the output voltage is not going to change, except for the fact that I am opening the loop. But in absolute, the single gains are not changing. So this is a good point to open the loop. If you remember, usually we can open the loop either where we have a high impedance or where we have a low impedance. Actually, this point here is a point at low impedance. So this is a good reason for opening the loop just here. Now what? I never remember. Okay, so actually once that we decided where to cut the loop, where we are going to cut the loop, we have to consider that we must calculate RO first, the output resistance at open loop, and then divide by the loop gain. So what I'm going to do is this. I go back to the previous slide. I want to see which is the output impedance seen by the load resistance. So if I watch into the circuit, if I look in this direction, I can neglect basically the resistance R1, R2. They will be also open, but in any case, they are very high. I can neglect the RD. This is a resistance which gives a constant current, let's say, to the Zener diode. So, considering that through this resistance there is basically a constant current can be seen in some way as a current generator, which is draining current. And when we study dynamically the system, we can open that current generator, basically. So we don't care about the resistance that is both high or can be neglected. So what is left is only this part of the circuit, if you see here. So what I can do for calculating this resistance is to apply a test voltage generator here at the output. And I have to measure the incoming current, Ix, the current that is getting into the system. If I take the ratio, I get the output resistance. I try to do a number of simplification. On this side, on the left, you see here there is a ground, while in the real circuit there is an equivalent battery. I go back, this one, VDC. But if you remember, when I want to measure resistance or something, I have to put a test generator and switch off all other independent generators. So turning off VDC means bringing it to 0, so short circuit basically. Okay, so what I have left here is only the filament resistance, R3, transistor Q2, the Zener diode, and something else that I am neglecting. And basically, once that we open the circuit, we cut the resistance, we are not sending any signal to the base of a transistor Q2. Dynamical signal. There will be a bias, a polarization, static polarization, but there is no dynamic signal that is going to transistor Q2. So if there is no dynamic signal going into transistor Q2, I can imagine that basically there is no signal in the collector. So no dynamic current in the collector, and the output of the collector is a current generator. If there is no signal, I can consider the collector like open. Okay. So there is only a static component in the collector current, but there is no variation. We are here in a dynamic circuit. So there is no variation. I can consider that the collector Q2 is basically open. Why am I saying all this stuff? Because now I can consider that here, then, the collector is open, basically. It's dynamically open. Because there is no signal at the input of the transistor, so no variation in the current of the collector transistor Q2. This means that all my circuit becomes something like the Vx, the current Ix, the transistor Q1, resistance R3, and R filament, and that's it. There's nothing more than this. Now I can also do this kind of consideration. If beacon X creates a current Ix, the current Ix will be splitted, let's say, into a base current and collector current. But due to the fact that the collector Q2 is open, on resistance R filament, the two currents will recombine and they will be equal again to Ix. You see, the current goes here, then splits from here and here, and then the two currents will recombine here. There are no other ways where this current can go. So the current Ix is the same as the current here on the filament resistance. And I can use this trick for trying to recover the values. So don't be afraid of the strange direction for those currents. Basically, Ix is the sum of IB1 and beta IB1, but I have to change the sign because they're going the other way. So I can write that IX can be written as minus IB1 plus beta IB1. Do you agree? That is minus IB1 times 1 plus beta 1. And that's the first result. If I want to consider the voltage Vx, I can calculate the voltage Vx in this way. I have to consider what is inside the resistance, inside the transistor Q1. And okay, if I took this path, ground, this path here, 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 and here, what is inside the transistor Q1 is basically R pi, R pi, between the base and the emitter. So I can calculate the total Vx as the sum of Ix, R filament, that is going this way, plus minus IB1 that multiplies R3 and R pi 1, because this current is going in the other way. Okay, so the total Vx can be written as the sum of Ix R filament, that is the voltage drop across R filament, plus the voltage drop across R3 and R pi, that is here. So that's the final formula. Again, I substitute from this relationship, I derive IB1, and I put the result here. So IB1 should be minus Ix over 1 plus beta 1, and I can put IB1 here. So what I get is Ix R filament plus, again, Ix over 1 plus beta 1, minus and minus cancel each other, times R pi 1 plus R3. Do you agree this is correct? Okay. So the output resistance RO is Vx over Ix, can be written as R filament, just Ix goes below, plus R pi 1 plus R3 or 1 plus beta 1. What I can anticipate is that, okay, I wrote this formula in this way, but we'll use this formula here at the bottom of the slide. If you consider that our filament is quite small, there are a few ohms. R pi, we are used to considering this resistance of the order of kilo ohms, but this is a power transistor which has low beta, and the current, the static current is going to be high. This means that the R pi will be small, in the order of ohms, tens or ohms. R3 should be high because we saw that we must increase R3 in order to get a good rejection to the ripple, input ripple. So this means that basically the only terms that remains here is R3 divided by what? 1 plus beta 1. 1 can be neglected, so basically we'll have something like R3 divided by beta here. We'll see that later again. But just in order to consider what is going to happen. I leave this result here, and I move to the other point. We must calculate the open loop gain of the circuit after we cut the wires here. So we open the circuit here. Can we calculate this open loop gain? What is the open loop gain? This gain is the ratio between the output voltage VO and the input voltage that will be again another test generator Vx placed here. Actually, in this schematic, I neglect again the VDC, because I must only put one independent test voltage generator and kill all other generators. But also for making things easier, I neglect the R filament. R filament should be in this point, just over the ground. It's small. Please allow me to neglect it. So I could have done that also before, but here it was a bit interesting to consider that the total current will be the same as here. So it was important. Okay, so we end up with this kind of circuit where we have this Vx independent test generator, the voltage divider R1, R2, the transistor Q2, the Zener diode on the meter of Q2. This was the wire for the resistance that supplied the current to the Zener. So we cannot consider. We can also neglect this. Then, if you remember, in the previous slides, we calculated that the collector current for transistor Q2 was GM capital Vx. And this GM considered everything: resistance R1, resistance R2, the dynamic resistance of Vz, the R pi, everything was inside this GM capital letter. Okay, so this means that for me it's easier, starting from the value of GM, to calculate the gain of the system. What is the gain of the system, basically? The gain of the system is, in this case, is simply given by the product of the current, the collector current of Q2, that is GM Vx, times what the collector sees. What is the resistance seen by the collector of Q2? We have R3, which is going to the ground, but we also have the resistance that we see looking into the base of transistor Q1. That means R pi plus 1 plus beta 1 times the load resistance that is on the meter. Okay. So I can suppose in this case, for instance, that this is a second resistance, the resistance seen by the base on the base of Q1 is larger than R3. In any way, if it is larger or comparable, more or less the total resistance that is seen can be compared to R3. Okay, if the data resistance is larger, the smaller resistance will be, in this case, R3. So I can say that the resistance seen by the collector Q2 is basically very similar to R3 in terms of value. So when I want to calculate the gain, sorry, but also I'm forgetting that given that Q1 is a collector connection, the voltage on the output will be the same as the voltage on the base. Probably I forgot to say this. Q1 is a common collector, so its gain is 1. The output voltage VO is the same as the voltage on the base of Q1. And the voltage on the base of Q1 has been calculated as the product of the current, the collector current of Q2 and the resistance seen by the collector, that is more or less R3. So if I want to calculate beta A, I can say that basically this beta A is equal to GM times R3. Okay? The output VO is GM R3 Vx. I divide by Vx, and so I get GM R3. Do you agree, or you don't like this? Okay. I see people with some strange faces. What don't you like here? Cosa non vi piace? Vedo. It's okay. No, if there is something that you don't like, please tell me now. Apart from some strange approximation, it should be more or less logic. The reason for doing the approximation is obviously for getting a very simple formula at the end. That's what we are going. So now, let's suppose that what we said is correct. We can obtain the closed loop output resistance if we divide the open loop output resistance RO that we calculated here by 1 plus beta A that we calculated here. And so I can write R output, that means with feedback, as the output resistance without feedback divided by 1 plus beta. That is the value for the output resistance that we calculated before, divided by 1 plus GMR3. Just following what I told you before, if I consider that R filament can be neglected, R pi is smaller than R3. So in the numerator here remains only R3. 1 can be neglected with respect to beta 1, so I got R3 over beta 1 on the numerator. On the denominator, 1 can be neglected, I hope, with respect to GMR3. So I get GMR3 on the denominator. R3 and R3, I can cut them. And so I get 1 divided by GM beta 1. So the output resistance of our system can be expressed in good approximation as 1 divided by GM beta 1. Okay. Now, apart from the number of approximation that we have done, there is only one more or less here. Approximation symbol is here. What is interesting in this formula? The formula tells us that if you want to reduce the output resistance, that means having an output voltage that does not depend on the output current, we must increase the denominator of this formula. One way, there are two ways. We can play with GM, but we can play also with beta 1. We already saw that playing with the GM is not very easy unless we add many other transistors. We can add something more if you want, also op amps and things like that. But we are still in the simple circuits. So the other way to play is to increase beta 1. How can we increase beta 1? Using a Darlington transistor, basically. Darlington transistor that is a combination of two transistors in cascade. There should be a slide soon after this one. Okay, so now we try to see how we can increase this beta. Can I change the slide? It's okay? Okay. Okay, go back.
La corrente per la resistenza vista non deve dare una negativa, cioè sicuramente con X per la resistenza che vedo
G con M.
Guarda che questo deve essere fatto. Io vedo una resistenza.
Sì.
È una funzione negativa però no.
Ok, yes. The feedback is negative, okay. Let me think about it. No, okay, one moment. It's negative. No, let me check. It's a negative feedback, so in any way there must be a minus in the loop. Okay. It's right. Okay. Devo confrontare il modello. Il fatto che sia negativa è giusto, perché noi comunque andiamo a sottrarre nell'anello la tensione. Questa negatività è quel meno che dovrebbe spuntare nel blocco. Ci possiamo ripensare? No, ok, no, ci ripenso. Ok, no, bisogna mettere assieme due pezzi di cosa. Dovrebbe funzionare perché la reazione comunque è negativa, quindi va bene. Ok. Quindi devo capire dal punto di vista formale questo segno meno dove ce lo spariamo. Questo è giusto. Ha ragione. Ok. So I was saying that I want to increase the beta. How can we increase the beta? This is the Darlington connection that I hope most of you have already seen, or all of you have seen. We consider a beta connection, a Darlington connection, when we have two transistors that are cascaded. In which way? We have a first transistor that is a small signal transistor, basically, where we introduce, we have a base current here that is amplified by the beta 1 of the transistor. And then we take the emitter current of this first transistor and we send it to the base of the second transistor. So the final current in the second transistor, Q1B, obviously this has to do with the collector current, but in this moment we are considering the collector and emitter current are more or less the same with a small error. So when I can say that the emitter current of the first transistor is beta 1 times the base current of the first transistor, and then this current becomes the base current of the second transistor. So the emitter or collector current of the second transistor will be beta 1 times beta 2 times the incoming current. Basically, we can also write, if you prefer, that if I have this current here, that is IB1, so the base current transistor 1, here I have a IB2 current, that if we want to be precise, it is 1 plus beta 1 times, it's very complicated, the current IB1. Okay. So the final emitter or collector current here, let's say IC2. IC2 is what? Is basically, it's very complicated to write with the mouse. It is beta 2 times the IB2. And IB2 is 1 plus beta 1 times the current IB1. So if you consider the total beta of this transistor as the ratio between IC2 and IB1, I get something that is more or less the product of beta 2 and beta 1. That's the formula, simplified formula that I wrote here. So with those Darlington connection, you have what they call a super transistor or Darlington transistor, whose beta is the product of the betas of the two transistors. I don't say exactly it is beta squared, because usually the first transistor is a small signal transistor, the second one is a power transistor. For small signal transistors, the beta is in the order of 150. For power transistor is in the order of 50. So you have to take the product of the two. Typical beta are something between, so for a Darlington, something between 1,000 and 10,000. So it can be very high. So this is the trick. We must change the output transistor Q1, and instead of Q1, we use a Darlington connection like this. Okay. And that's what we can do for increase, as I said before, for increasing this beta 1. The other point that we saw in the past was the opportunity, instead of increasing, the resistor R3, that is this resistor here. This was interesting, apart that for simplifying this formula, it was interesting also for improving the stability factor in terms of the input ripple. How can we substitute this R3 with the current generator? One way would be to use a current mirror. We can do that with the current mirror, but don't forget that here we are considering a discrete transistor circuit. So transistor where we are soldering together single components. It's not an integrated circuit still. So if I take, instead of using R3, I use a current mirror, I need 2 transistors. While if I use the simple circuit here, I can do that with only 1 transistor and a Zener diode. This is a simplified version of a current mirror, if you want. Or anyway, a circuit that is able to give a constant current. How does it work? In a very simple way. We have an input voltage that is Vin. And what we do here is basically to bias a Zener diode. Again, we can consider a 0 base current. Okay. So we can consider a 0 base current for the transistor just in order to simplify things. We have V in here. This Zener diode is correctly biased. So across the Zener diode, there is a voltage that is more or less Vz. Okay. We don't need to consider a more complicated circuit than this. We are used to have usually a resistor on top and a Zener diode on bottom. In this case, they are placed in the other way, but they still work fine. So once the Zener diode is biased, is reverse biased, the the voltage across the Vz is Vz itself. Then we have a PNP transistor. The PNP transistor has a VB voltage that is reversed if we consider what you are used to have. So in simple words, what have I done? I push the dot, punto, and switch off everything. I've never seen that. Sorry. Okay, so if we, let me use the pen. So if I consider the VB voltage, please allow me to write it like this. We have 0.7 volts with the positive on the emitter this time, just because we are considered a PNP transistor. Okay, so if Vz is the voltage between Vin and the base of the transistor, what is the voltage across Re, the emitter resistance of the transistor? Is Vz plus or minus in modulus 0.7. So if the Zener diode, for instance, is, let's say, 5 volts in total, from here to here, the voltage across the resistor is 5 volts minus 0.7. If I divide this voltage, Vz minus 0.7, times by the emitter resistance Re, the system will do everything for keeping this relationship constant all the time. And so I can impose the emitter, and so the collector current of the transistor itself. So the current under the collector of the transistor will be Vz minus 0.7 divided by Re. And that's it. We can design how much current we want. This is the current I3 that is going to bias this part of the circuit. It is a static current. But even if the input voltage changes, this current is not going to change. The current I3 is not going to change. So if there is some ripple in the input voltage, and we suppose that more or less the Zener diode doesn't change its current and its voltage, the current I3 is not sensitive to the input ripple voltage. It's a constant current. So we are not transmitting a ripple down here. Or in a more formal way, if I consider the dynamic resistance seen by the collector of this transistor, is the dynamic resistance seen by collector, so it tends to be very high. And it represents the equivalent resistance R3 of our circuit. So I just take off R3 and I put this part of the circuit in the new schematic. Ok? Sta facendo la domanda? Forse. Mi sono risposto. Okay, now the point is already pointed out here. We may have a problem with temperature due to the base voltage change of this transistor here. The change in the temperature of this transistor here are here, minus 0.7, within this minus 0.7. So if we want to keep the voltage across the resistor constant, we must keep constant this number here. If the 0.7 voltage is going to decrease, we must decrease also the VZ. So the difference will be constant. If we want a VZ that decreases, we must use a 3.3 volts, because the decrease of this voltage is the same as the decrease of the base emitter voltage of the transistor. So we are forced to use this 3.3 volts Zener diode here. And the system, this part of the system will be thermally compensated. Okay. So a circuit that is a bit more complicated than what we saw before, but is much, much better, is this one, where we have done what? We have changed the output transistor from a single transistor to the Darlington transistor, and we have added a sort of current generator here in order to increase the resistance R3, the equivalent R3 resistance that is not present here, but is given by all this block here. So now we need what? 4 transistors, well, or let's say 3, because we can buy directly a Darlington transistor. If you want, you can buy a single transistor which has 3 terminals, as you see here, but has a Darlington configuration at the, inside of the case. The system is also thermally compensated because we compensated the variation of VB2, of Q2, using a 6.2 volts Zener diode, and we compensated the variation of transistor Q3 using this 3.3 Zener diode here. We don't care about the voltage variation of transistor, the Darlington transistor. By the way, here the voltage variation, what is the voltage variation with temperature for this Darlington? It should be 4.4 millivolts per Celsius, because it's given by the series of the 2 base emitter junctions. We don't care about this because the feedback will adjust everything. The feedback controls the output voltage and compares it with the Zener diode. So if something goes wrong, it will adjust. So we don't care about this transistor. And you have to consider that this transistor here is heating a lot. It's becoming very hot. Sometimes you cannot touch the transistor because it's 50, 60 degrees, even 100 degrees, depending on how you design the system. But we don't care. So if we, let's say, if we increase by 10 volts, we are going to vary by 40 millivolts the VB here, the 10 volts, 10 degrees, sorry. If I increase the temperature of this Darlington transistor by 10 degrees, the base to emitter voltage will increase by 44 millivolts. That is not negligible. If we increase by 30 degrees, we will increase by 120 and more millivolts. So that is a large variation. But we don't care. The feedback adjusts everything. Okay. Più alta. Ecco, una distanza di...
Perché ha scritto che SB aumenta?
Finisce.
Nella slide precedente ha scritto increase, invece increase.
Aspetta.
Quindi
That's wrong. No, okay. So, no, I wrote the slide, I didn't read them. Okay, so, okay. No, okay, this is wrong, definitely. Okay, so it is, this case, decrease. Okay, you are right. So this, okay, decrease, I put an arrow going down, okay, because it's too complicated to write decrease, otherwise it must go out. So, okay, so I have to fix this. Right. Okay. Some of those slides were made last year, typically between midnight and 2 or 3 o'clock in the morning. So some mistakes are there. Okay, I told you something about the fact that the series transistor is heating. As I explained to you a longer time ago, the system basically works in which way? It is a series pass regulator. It means that the transistor, the series pass transistor, simply changes its equivalent resistance in order to have a voltage divider made by the transistor and the load, and we want to keep the output voltage constant. So I can say that more or less, in first approximation, the equivalent resistance of this transistor is comparable to the load resistance. Just an example, if we have a VDC of 20 volt and I want a 10 volt output for a certain current IL, you can imagine that the equivalent value of this transistor must be, in terms of resistance, must be the same as the load. So that we have a 1 to 2 voltage divider. We enter with 20 volt, we have the same resistance here, and the output will be 10 volts. So this is an example that let me understand that in this situation, for instance, we have the same power dissipation in the load and in the power series pass transistor. So if I want to divide the voltage from 20 at the input to 10 at the output, given that the IL current is the same in the load and more or less in the transistor, the load and the transistor will dissipate the same power because they have the same value in terms of resistance that I see in this direction. And this is a very interesting point. As I said, the main problem with the series pass transistor is that it is heating a lot. And just if we want to visualize it in a better way, we can say what? We have this situation where Vin is the input voltage. Then we have a VCE of transistor I1B. This transistor here. I can express this VC in this way. That's VCE of this transistor 1B. It's very complicated, right? Okay. So the input voltage is given by the sum of VC of this transistor plus the output voltage. Here it's written that the collector emitter voltage of this transistor is the difference between the in and the out. But transistor and load have the same current. There are only a very small difference, but they are basically the same. So what I can do is a graph like this, where I put in vertical voltages, in the horizontal axis the current. This is the current which goes to the load, IL. And here can I indicate which is the output voltage on the load, this green line. But here I can also indicate the input voltage, Vin. The difference between Vin and Vout is the VCA of the transistor, collector emitter voltage. So From V in to V out is the collector emitter voltage of the transistor. V out is the voltage on the load resistor. And in this case, for instance, I can also indicate that it's a linear load, a resistance. So I can use this red line to indicate the load line of corresponding to the resistance. If I send the voltage VO, the resistance will allow a current IL. Okay. The two areas, VO times IL and Vin times IL, but also Vin minus VO times IL, represents the power dissipated in the transistor. That's the blue line, blue area. The green line area instead is the power dissipated in the load. So this graph is very interesting because it's a simple way to visualize what is the situation depending on how the load changes. If I change the value of the resistance, for instance, I do what? If I decrease the resistance, the line will go down, will turn this way, because it means that for a fixed V out, the current will increase. Okay. And so, actually, depending on how much current is passing, I can visualize what is the amount of power dissipated in the transistor, as I told you, and the load. What we can see here is that basically, if on the other way, I increase the value of the load resistance, it behaves like a line that goes in this direction. This means that we have less current and less dissipation, both on the load and on the transistor. So in absolute, the situation which is safer for the transistor is when no current is taken, when there is no load. So if you consider an infinite load, resistance with an infinite value, this infinite resistance corresponds to a vertical line. That means no current, and so there is no dissipation both in the transistor and in the load, which is different from the parallel configuration, if you remember. When we studied the parallel voltage regulators, when the parallel voltage regulator is a simple Zener diode. When there is no load connected after the Zener diode, all the power is being dissipated in the Zener. Here, instead, it works in a different way. If we increase the current taken by the load, we also increase the dissipation in the transistor. There is also another point. What we are able to change the output voltage of the power supply because we introduced a knob, a variable resistor that is able to change the output voltage. Well, for a given current, if I have a load that can absorb certain current, and if I reduce the voltage, obviously the load will change to keep the current constant. But you see that when I work with the low voltages, the power dissipated in the transistor increases. This means that the worst situation for such a power supply are those where the power supply is given the lowest voltage. So for a given current, the lower the voltage, the output voltage, the higher the power dissipated in the transistor. So actually, when I design the circuit, I must take care that the system can sometimes work in strange ways. Okay. And actually, for instance, quello, come si dice, non so, in inglese è la meno spesa, diciamo. Well, here, no, okay. No, your colleague is saying that if we increase, for instance, the current, also there is a higher ripple, and so. But the problem now is much. The problem now is much worse. So we are dissipating a lot of power in the transistor, And just before I change, that's the reason why they are also called dissipative regulators. Because in this kind of regulator, we dissipate a lot of power. But that's a price that we must pay for having a good output voltage. Just to let you understand, this series pass voltage regulator or dissipative regulator, or also they are called the linear regulator, because we are basically using transistor in their linear region, have a very bad pure efficiency. The switching power supplies, that one that you studied with Professor Vital, have a much better performance in terms of power dissipation, efficiency, and so on. But they generate a lot of noise. While these power supplies that we are studying here, they virtually generate no noise. So in very good equipment, for instance, in very good radio receivers, for instance, you don't want to use a switching power supply. You want to use a linear power supply. You don't care if the system has a poor performance in terms of efficiency, but if you want to be able, with a radio, to pick up very low noise, very low signals from distant transmitters, you need to have a system which has no noise. And in this case, you start with a linear power supply, which generates almost no noise. You're not going to use a switching power supplies that as soon as you switch it on will generate a mass of noise at any frequency. It's like killing yourself, okay? Committing suicide, you should do something. Imagine that you have a radio telescope that wants to pick up the signals from far galaxies and things. You are not using a switching power supply for that system. Okay. Now, we must take care about the poor transistor. The transistor must be used with some moderation, let's say. Why? Because the transistor can die if we don't take care of the transistor, or the series pass transistor. I'm talking about this transistor here. It can suffer by a number of problems, which are depicted in this nice picture. It's an approximate picture, but one sort of picture like this is usually given for all power transistors. We must take care that the maximum collector current is not higher than this IC max. Why? Because otherwise we are probably going to melt the wires which connect the chip to the terminals. Or also current higher than this. So that's the limit. You can use a current that must be lower than this. You see, this is basically the output characteristic of the transistor. I forgot to tell that. That is IC, the collector current, versus the VC voltage of the transistor. So here we have all the characteristics, the output characteristic of the transistor, that are not depicted here. So first of all, take care that maximum collector current must not be overtaken. Usually, when you take look at the data sheet, they say maximum collector current is 10 ampere, something like that, or 20, depends on the transistor. Okay. So if we go over this current, we can melt the wires, basically. Then there is a thermal dissipation. This curve number 2 is a hyperbola. It's a hyperbolic plot. Why a hyperbolic plot? Because if you consider this graph here, you can consider points where you have constant dissipation. A constant dissipation means that the product IC times VC is a constant P. You can plot a number of hyperbolas on this plot. Each one will tell you which is the current power dissipation. The power dissipation through the thermal resistance of the chip, of the device, gives the temperature increase in the device. I don't know if in some of your subjects you studied something about thermal propagation. Basically, you can define a chip, a die to ambient resistance. And if you multiply this resistance times the power, you can get the temperature increase in the chip. And the chip of this transistor usually must never go over 120, 150 degrees. Otherwise, the transistor stops working or starts to work in a bad way. Remember that the doping in the transistor are the reason why the transistor works. If you increase too much the temperature in a transistor, you'll have so much thermal generation of holes, electron couples, that all the doping will disappear, basically. And the transistor dies or works in a bad way. So this is interesting for thermal dissipation. Then if you take some books, they talk also about the second breakdown limit. This is a different formula. You see, you have IC times VC to a alpha coefficient power. So this means that this is, it's not an hyperbola, it's something slightly different curve. This seems to be due to the fact that if you have a very high current and voltage, the current can concentrate in defects in the crystal of the transistor, especially if you have some defects on the surface of the chip. In that case, the current tends to concentrate in those, let's say, holes. A defect is a recombination point where the carriers can recombine. This increases the temperature at such a level that the die can melt. So you can melt the junction just because the current concentrated in some, let's say, hot spots, defects, crystal defects, okay? So it's better if we keep far from this limit here. The last limit is the VC max that induces an avalanche breakdown. You are transforming your transistor into a Zener diode, but the transistor is not designed for working in that situation, so basically it will die. You see, it means that when you decide your circuit, you must be sure that all the operating points will be here. That's the reason why this area is called the safe operating area, SOA, for a BJT. Come on? No. You must be sure that the operating point, il punto di riposo del transistor, di funzionamento, is always within this area. So one of the problems that we have seen is due to the thermal dissipation. That is this curve here. How can we reduce the temperature of the transistor? Most of the time, we connect the transistor to a heat sink. Simple heat sink, or heat sink with a fan. Or sometimes even to some kind of heat sink that are using a liquid coolant. Liquid coolant, un refrigerante. If you open the PC, you will find what they call a heat pipe. Heat pipes are some tubes made of copper, inside which there is some liquid that basically evaporates when it's on the chip, navigates inside the pipes, and the fan is somewhere else. For instance, the chip is here, the CPU is here, and the fan is here. So these heat pipes bring the heat from here to here. It's like a sort of small air conditioner. It's working on the same principle of the air conditioning without having a pump. But it's a pump which works by itself, okay? That's a big problem because you must take off the heat from the hot spots and bring it out. So usually, come on? See, no, a large. It's like in the car that you have the radiator. Okay, no, it works in the same way. Otherwise, the chip will die. Let me see it. Can you survive for a few more minutes? Because if we stop now, we'll stop forever. Okay, so if you can survive 15, 20 minutes, then we'll stop here early. Okay, we do this. Now it's something quite easy to understand. So let me see if I forgot something. Okay, no. The transistor must be without the within the safe operating area all the time, cooling down, blah, 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 it's single max. Okay, I go further. Don't be afraid. This is a very interesting point. What is the problem that now we are going to face? Once that we designed such a nice... Okay. Once that we defined such a nice power supply, there are a number of problems. What are the problems? If you are working with your power supply and you are connecting the power supply to some utility, you are charging a PC, a cell phone, what you want, it is something quite that happens quite often is that maybe you have a screwdriver in your hand, or your friend has a screwdriver in your hand and drops the screwdriver on your circuit, creating a very nice short circuit in your circuit. So what we want to do is to try to protect our power supply from short circuits. Why should we protect this? Or maybe sometimes what happens is also, I don't know, the battery of the cell phone is shorted, and so you have a short circuit at the output of the power this power supply. How can we protect the power supply from short circuit? Consider what you're going to do if you play in a lab where you're testing circuits. It may happen that you forgot a wire or you drop a screwdriver and you make a very nice short circuit. So can we protect the power supply from short circuit? Let's see how we can do that. What is the problem with the short circuits? It's represented here. Basically, you are reducing the load resistance from its initial value to a very low value. So here I'm considering that the current is not increasing. Let's trust this. Simply because we are reducing the voltage, a short circuit basically brings this line down to the horizontal line. So we have 0 voltage with this IL current. What happens is that all the power is being dissipated in the series pass transistor. Okay, this blue line, green line goes down to 0. You have no voltage on the load, but all the V in the voltage is across the VC voltage of the transistor. So you increase at the most highest level the power dissipated in the transistor. But also, if you may create a very good power supply, it is possible that the system, just because it wants to react to this decrease in the output voltage, the system will try to push a lot of current in order to increase again the voltage. This means that the working with this line, the IL, at the same time will increase. The system has a negative feedback. If you are creating a short circuit, the output voltage goes to 0. The negative feedback tries to push more current to increase the output voltage. So this means that you are not only having 0 voltage at the output, but you're also increasing the output current. So this area increases a lot, and you can destroy instantaneously the transistor. So this is very dangerous. We should find some way to limit the current, to limit the dissipation, and to preserve the power supply. This can be done simply adding one resistance and one transistor. So we open... It's a bit cold. Grazie. Okay. So what we can... Prego, someone speaking? Okay. From home? No. Simply what we have done is to take the output circuit and try to introduce some way, somewhere, I say here, so we cut the wire here, and we introduce this couple of transistor series resistance. Okay. Then I will explain you why I added it here and not here. It will work the same way unless that we have a small problem. So let's make sure that we cut here and we introduce that circuit here. How does the circuit work? Basically, it is a sensor resistor and a small signal transistor we connect with base on close to the output series pass transistor, and the emitter instead is on the load. The collector of the transistor is on the base of the series pass transistor. So if we have Darlington is on the base of the first transistor, otherwise if we don't have Darlington simple transistor, it will be just between the base of Q1 and the collector of Q2, this point here. How does it work? Well, basically, if the output current, IL, is so small that the voltage drop across the R sense is below 0.6 volts, transistor Q sense, it's open, and we don't see anything. Ok? Sta piovendo, ci approvvigniamo alle 2, quindi giustamente io. Ok, no, it's raining here. That's... Ok. No, sì, potrebbe essere messo anche... No, noi lo mettiamo prima del partitore. Our colleague was asking why do we put this sense circuit here and not here? Just we'll discover at the end. Okay, so don't think it is about it. I'm just telling you that I prefer to put it here. Okay, at the end we'll discover why. Okay, so I was saying, if the IL current is low, we don't have a voltage drop here that is higher than 0.6 volts. So this transistor is switched off, and the system, the Q sense doesn't work. So we don't have any change with respect to what we have seen before. But if for a certain value of IL, we reach 0.6 volts across the R sense, this transistor will start working. What it does is to take some of the current that usually goes on the base of Q1 and bypass this current in this direction, from collector to emitter to the output. We are talking here about a very small current, a few milliamps. These few milliamps will be multiplied by beta square, let's say, by beta 1, beta 2, and so they will become amperes here. But if we remove a few milliamps of the base current of the series pass transistor, we are going to reduce the current that it will generate, that will pass here. So basically what we do is, we have, look at this plot here. This is the output current of our power supply, the input voltage and output voltage. We decide to turn on the transistor, the sensor transistor, at a current value that we call I threshold. Okay, usually, if I read here, the I threshold is around 1.5 volts, times, sorry, volts sta per volte, 1.5 times what we call the nominal current for the power supply. For instance, we buy a power supply for a cell phone. We buy a power supply which should give 1 amp. Okay, I design the threshold current at 1.5 amps. So that's a situation that usually should not happen. But if for some reason the current goes over 1.5 amps, the system will react. How? This transistor here will drain the current from the series pass transistor, so it will force the transistor to reduce the current that is passing. It's a dynamic system where actually if this transistor reduces too much the current, we will have a voltage on our sense which will be below VB. So actually where the system stabilizes is on a point where the current passing through the transistor is basically the threshold current. So that's the reason why I plotted this stuff here. This graph means that if I have a load is represented by this line, red line here, okay? So let's suppose that we have first a load with a value, resistance value, that is, I should change the color, so, one moment sotto. Pointer option, shrink color, che ci mettiamo qua. Giallo non si vede, villa. Okay, I'll use this color. Okay, let's suppose that first we have a high resistor with this slope here. This means that in normal operation, the current passing through the power supply is this value here. It's in a safe area. The system does not turns on the protection system. So if the resistance changes, the output resistance changes, we can have a constant output voltage with different currents. But when we reach the threshold current, so if the load resistance reduces its value, at the point when we have a current passing through higher or similar to the threshold current, this transistor turns on. And it starts limiting the current. What can happen is simply that if I reduce further the output resistance, this transistor is limiting its current, but basically the current remains constant. What we have is only a reduction in the output voltage. So that's the reason why we call this a constant current short circuit protection. Because once that the protection turns on, the system will limit the current more or less to the threshold current, even if the output voltage is going down. For a perfect short circuit, we'll have a line that is horizontal. This means that we'll have zero voltage, but the current that is, the maximum current is equal more or less to the threshold current. In this situation, all the power will be dissipated by the series pass transistor. But now we know exactly which is the maximum power that can be dissipated by the system when it is short-circuited. Okay, so we can design everything in order to withstand, to last forever, even with a short circuit. Okay, so our system is in a short circuit situation. Anyway, the series pass transistor is designed to survive to this situation. When we realize what is the problem, maybe it's the load that is short circuit, maybe it was the famous screwdriver fallen, cacciavite, fallen on our circuit, we remove the screwdriver and the system will start working again. Because we have not destroyed the series pass transistor. Okay. So this is a very simple and important circuit that is used almost everywhere for limiting the maximum current. If you want, at the same price, we have also gained a different way of using a power supply. Because if, for instance, if we can regulate the threshold current, we can decide to use this circuit not only as a constant voltage power supply, but also as a constant current power supply. So if our load is so small that we are working this vertical part of the characteristic, and if we are able to change the position of this threshold, we can move this green line to the left or to the right. Usually, professional power supplies have two knobs, one for regulating the output voltage, and the second one for regulating the threshold current for the short circuit protection. Because sometimes I want to use this particular feature for recharging the batteries of my cell phone. batteries of cell phone, especially if you are talking about nickel cadmium or nickel metal hydride batteries, these are the lithium are a bit more tricky and dangerous. But for all the batteries like the nickel metal hydride, you can use this situation because for recharging batteries, you need a constant current source, and you will charge your batteries for typically 14 or 7 hours or something like that, 10 hours. But you know how much current you're sending, you know which is the capacitance of the battery, and you just make your calculation and keep this situation for charging the batteries. Why do I use a constant current charger? Because during the charging of the batteries, the voltage in the batteries can change, but I must be sure to send an exact number of electrons inside of electrons inside the battery. So in this case, the system will adapt automatically to the output voltage. You see, if you're working the vertical line, you can accept different output voltage, but the current is constant. That's a very good current source. So that's why in those linear power supplies, you usually have two knobs, one for the current and one is for the power. Also, for instance, if you're in a lab and you're going to test a circuit that you have done by yourself, maybe there is some error. So in this case, you know more or less which should be the current absorbed by the circuit if it works fine. But if it doesn't work fine, you can destroy the circuit. So in this case, you are going to limit to the threshold current to a current which is slightly higher than what you expect. My circuit should absorb 100 milliamps. I set a threshold at 120. If something is wrong, I limit the current. Otherwise, I will destroy everything. So that's the reason why also you have the possibility also to set the maximum current in your power supply. Good power supply usually have this trick, okay? This is a variation of that circuit. I just want to show you how it works, then we'll see how it is made, because now we are a bit tired, okay? This is what second short circuit protection that is called fold-back circuit. The previous one was the constant current circuit. The second one is the fold-back circuit. What is a fold-back circuit? Basically, in the fold-back circuit, once that you understand that there is some fault, that the current is going too high, you not only keep the current constant, but as soon as the output voltage decreases, you will also reduce the output current. So the system is able, depending on the output voltage, is able to reduce the short circuit current. So if the output voltage goes to 0, the system will give a short circuit current that is much less than the threshold. Why is this important? Because in this case, again, the worst case situation is the short circuit. When we have a short circuit, if we decrease the current that is passing through the series pass transistor, we are protecting the transistor itself. In a constant current system, we will have that large area as the power dissipated in our output transistor. But if we have a fold-back circuit, when we have a short circuit, the area will be this one, that is smaller. So we are able to protect in some way the transistor more than with the constant current. This means that when we design the system for managing short circuit, we can use a smaller heatsink and smaller transistors. So that's why it's important in good systems that they do this trick, okay? Okay, if you don't mind, I mean, now we are a bit tired, so it's not time for looking in detail into this circuit. So I will say that we stop now and we meet again on tomorrow.
Professore?
Just tomorrow, so on Friday, okay?
Professore?
Sì, prego, mi dica.
Il fatto che noi comunque posizioniamo in particolare quello della corrente costante prima dell'altra retroazione è perché così in caso io risolvo prima il problema, prima che la retroazione faccia
Okay. Just last thing. Your colleague was right. Was remembering me that something that I was forgetting. Why we said so many times that this sense resistor and circuit will be placed here and not here? Because if we put this sense resistor here, the sense resistor will give a voltage drop. So there will be a voltage drop across the sense resistor. If we put the feedback system after the resistor, we can compensate this variation. While if we put the sense circuit here, the output voltage will change, but the system will not realize that there is a voltage change. So we introduce this sense before the feedback, and so the feedback will compensate also the voltage drop across the R sense, okay? Thank you for remembering.
Sì, figuri professore, perché quello continua praticamente, se io metto il feedback prima, quello continua ad aggiustare, ma
esatto,
il senso se ne accorge. E quindi
anche se c'è quella caduta. Sì.
Ok, va bene.
Ok, grazie
professore.
per averlo ricordato, grazie. Ci vediamo domani, see you tomorrow. Ok.
Arrivederci professore, arrivederci.
Bye to everybody. Ok.